Hi everyone, a very good morning to all of you. Are you able to listen my voice? Are you able to see the screen? Raise your hand. Okay. Now, so once again a very good morning to all of you. Let us discuss about what we studied in last class. Then we'll try to continue. So what we learned in last class is the first thing is what is the electric field? What is the electric field due to a dipole at any random point? That is what we have discussed first. So the very first thing what we have discussed is what is the electric field due to a dipole at any random point, where we got the electric field as Kp by r cube. Kp by r cube under root 3 cos square theta plus 1. So this is the electric field due to a dipole at any random point. Like if this is the dipole, minus charge plus charge, and this is the midpoint at any random point at an angle theta. So the electric field is E. That is what we have studied. And in this case, if you consider theta 0, then you will get axial point. If you take theta 90, then you will get equatorial point. See this one. So this is equatorial line, means theta 90 in this equation. If theta 0 means this is the line, that is axial line. So if you remember this one formula, you can get the electric field due to dipole on the equatorial line as well as on the axial line. Also, we have solved few questions. We have solved numericals based on miscellaneous concepts from the beginning, like what is electric force, what is principle of superposition, what is the electric field due to a point charge, what is the field due to system of point charges, and what is electric dipole, everything, dipole moment. So all those questions we have seen. Now, today what we are going to study is first introduction of continuous charge. See, I will tell you in a simple manner. Till now what we have studied is there is a point charge or there is a big charge, but the point from the body is very far, so that we considered this as like a point. So in all the numericals, in all the questions, what we considered is the point is at very far distance from the charged body, so that the charged body we have taken as point mass, point charge, point charge. So we treated every charge like a point, and at any distance r we found what is the electric field. If at any distance another charge is there, what is the electrostatic force experienced by that charge? That we calculated, Coulomb's law. But everywhere we said all the charges are like a point charges. Now suppose there is one body, continuous mass means the mass distributed over particular region, maybe in terms of length, maybe in terms of length. One is in terms of length, in terms of area, in terms of volume. See, these are the three things we can calculate. Suppose there is a wire. The charge is distributed over its length, means the body charge is not at one point, it is distributed over the length, particular length. That is called continuous charge distribution. Or you take a disc or plate, square plate or rectangular plate or circular plate, anything. So now the charge will be distributed through particular surface area. That's why it is called continuous charge distribution. The charge distributed continuously over a length, over a area, or you consider sphere. So sphere means what will be there? Volume will be there. So over a volume. So the charge can be distributed over the length and area and volume. So that case, the charge is not located at one point. The charge distributed over many points together as a length, as a area, as a volume. Then we call it as continuous charge distribution. So here I am showing you simple diagram. See here. So there is a line charge first. So this is the line charge. This is the surface charge. This is the volume charge. So there is one line charge means charge distributed over a length. So that Q charge distributed over a length L. Area means Q charge distributed over a area A. Volume means Q charge distributed over a volume V. Now here what we study here based on this is how to compute the electric field. That is what important, but that we study later. Just introduction I am giving. What is the meaning of continuous charge distribution? So based on this, how to understand the concept, how to derive the equations, how to solve the numericals, everything we study in detail. So what are all the elements are there in our syllabus and how to find the field due to that continuous charge distribution. Because here, suppose this line charge you consider. If there is a point charge, then we know at any point what is the electric field. But here so many such points are there. So that means you cannot apply the formula whatever we have learned already. So that's why here we need to apply something else. So what formula we need to apply? How to apply? How to find the field due to this total charge? Now the charge is not at one point. It is over a particular length, over a particular area, over a particular volume. So those questions we will study later. Now today related to this only, before understanding what is the field due to continuous charge distribution, let us define one more definition also here, same thing. See here continuous charge distribution means, as I said, there are three types. One is volume, another one is surface, another one is line. Line charge or linear charge nothing but length. So here first you consider linear charge distribution means charge distributed over particular length. So this is the length L and a charge Q distributed, then you can find the ratio of charge by length. The total charge distributed over particular length. So that is called charge density. In the same way here in the second case, the charge Q distributed over a area A. So charge by area, we can define one more quantity. Here a charge Q distributed over a volume V. So I can define charge by volume. So the first one is called charge per unit length. This is charge per unit area. This is called charge per unit volume. So charge per unit length is called linear charge density. Charge per unit area we call it as surface charge density. Charge per unit volume is called volume charge density. Till now we have seen two kinds of densities. One is mass by volume, that is volume mass density. Volume mass density. See, I told you many times, density nothing but always by volume only. We have discussed it already. There is also density in terms of area. There is also density in terms of length. We have discussed in the first PU. We have discussed in the waves. We have discussed in the Young's modulus. So, the density means you have to divide one quantity with either length or area or volume. If you divide with length, it is linear density. If you divide with area, it is surface density. If you divide with volume, it is volume density. But what quantity you are dividing, that density it will become. Mass by volume means volume mass density. Mass by area means area mass density. Mass by length means linear mass density. Like that here, now which quantity we are distributing? Not mass, charge. So that charge by length. Length means linear. Here which quantity? Charge. So linear charge density. So line of charge. Charge per unit length, that we represent with a symbol lambda. So lambda means charge per unit length. Similarly, charge per unit area, that is sigma, that is Q by A. Similarly, charge per unit volume, that is rho, that is Q by V. So these are the three densities in case of charge distribution. So this is what? The simple definition about line charge and surface charge and volume charge. Only you think about definitions. We will discuss in detail in further classes how to use these things, how to calculate these things and all, everything. See here. Here one more for the note verification also I have given. So for any line, see here the charge, some positive charge is distributed over particular length. So that when you consider one small element of length dl, now on this small element, let's take the charge is dq, the length is dl, and as it is line charge, what will be there? Lambda. So lambda equal to dq by dl implies dq equal to what? Lambda dl. So the small charge on small length is lambda dl. Similarly, when you consider surface distribution, see when you consider one big body, this is one big surface. Now within that you consider one small surface area, small surface area ds, having charge dq, then charge by area is called what? Sigma. So that dq, small charge on small area means sigma ds. Or you can also write sigma dA. dA or ds is what? Small area. So sigma is total charge by total area, and for small area, what is the charge? It is like cross multiplication. See here, total charge is q, total area suppose A, then dq is small charge for small area dA, then you cross multiply it, then dq equal to q by A into dA, cross multiply it. But q by A already we defined what it is? Sigma. So these things will be there. We will see further how we use them. Just definition I am telling again. Similarly, now you consider volume distribution also. There is a total volume V. There is a total charge Q. So what is the volume charge density? Q by V. Now if you consider a small volume dV where the charge is dq, then dq equal to what? Rho dV. So that is what? The volume charge distribution. Like that, the charge distribution is of three types. So linear charge distribution, surface or area charge distribution, or volume charge distribution. So three types of charge distribution will be there. Now you can get sometimes direct question. See here, one example I have given. What charge would be required to electrify a sphere of radius 25 centimeter? One sphere is there, radius 25 centimeter, nothing but 25 into 10 power minus 2 meter. So as to get a surface charge density, sigma value they have given, that is 3 by pi coulomb per meter square. Why? Because lambda means Q by L. So coulomb per meter. Sigma means Q by A. Q means coulomb, area means meter square. Rho is Q by V. That means coulomb per meter cube. So here sigma value they have given. Now what charge they are asking? Here as sigma value they have given, what is the sigma equal to? Just before we have defined Q by A. Then what is Q will become? Sigma into A. It is what kind of body? Sphere. What is the area of the sphere? Surface area formula 4 pi r square. They are not asking density. Suppose volume density. Suppose for the same question, instead of surface charge, they have given volume charge. Suppose for the sphere. So they have given volume charge means then you will define Q by V. Then Q equal to rho into V. So rho into V means how much? 4 by 3 pi r cube. If they give volume charge distribution. But here in the question, they have not given volume density. They have given surface charge density. That's why what formula I have taken? Sigma. So direct questions they can ask based on lambda, sigma, rho. And what are all the elements are there in our syllabus, that also we study in further classes. So here final conclusion is the continuous charge distribution means charge distributed over length. So Q by L linear charge density. Next, charge distributed over area. So Q by A is surface charge density. Charge distributed over volume, Q by V, that is volume charge density. So that way you need to understand. Now, the next thing here, what we need to understand is electric field lines. What is the meaning of electric field line? Means here, there is a suppose charge, or there are two charges, there are three charges. Minimum one charge is there means in the surroundings there is some electric field at any point you consider. At every point there is some electric field. If two charges are there, three charges are there. So in a region, if electric field is there, then at any one point there must be direction also. Either this or this, some particular direction will be there. So the region of electric field always we imagine in the form of lines. So there is a field, that means we imagine in the form of lines. So there is a space called completely filled with electric field. Then that region we represent with a lines, field lines, and imaginary lines. They does not exist. They won't exist actually. They are just like an imaginary lines. We imagine such that, see here, a field line is drawn tangential to the net at point. Thus, at any point, the tangent to the electric field line matches the direction of the electric field. What does that mean is, in the region of electric field, you need to imagine one line. You need to imagine few lines such that at any one point, suppose this is the field line, suppose I am telling. At this point, if you draw tangent to that line, that is the direction of electric field. Suppose at this point, if you draw tangent, this is the direction of electric field. Suppose this is the tangent at this point, this is the electric field direction. You need to imagine few lines such that at any point if you draw tangent to that line, that will give the direction of electric field. Such lines we call it as what? Electric field lines. Like here you see, electric field line describe the nature of electric field, and we can easily reveal direction, strength and other properties of electric field. From the field line shown in a particular diagram, you can say the direction, you can say the strength, you can say the nature of the charge. Like here, what they define is, suppose there is a positive charge. Now at any point, the field is away from it. At any point, the field is away from it, like this. So if there is only one charge, no confusion. Suppose if there is a negative charge, at any point field line is towards. So these lines only we call it as electric field lines, like this. So here let's take one positive charge. Now keep on represent the field lines. Like this. So there are so many electric field lines you can draw. If with the same case with the negative charge means the direction will become reverse, like this. Now these are all called what? Field lines. But if there is a combination of charge, then how the field lines look like, that is important. So there are 2-3 combinations in our syllabus. Those field lines you need to remember. Here for positive charge and negative charge, already we studied this, how the field direction will be there. Those field direction only if you imagine like lines, those only we call it as electric field lines. Those only we call it as electric field lines. Like here I am representing for positive charge away, for negative charge towards. So that is what we call it as electric field lines. Now if you consider the electric field lines, what are the properties? You need to remember. First one, electric field lines start on positive charge and end on negative charge. As I said, if there is a positive charge, the field direction away, so that's why field line away from positive charge. So away from positive charge means it looks like starting from positive charge, originate from positive charge. But if you take negative charge, it looks like it is coming on negative charge. That means it will end on negative charge. It looks like start on positive charge and end on negative charge. That's why the field line looks like originate from positive charge and end on negative charge. Now the number of lines starting or ending is proportional to the magnitude of charge. Yes. See, if there is a charge, greater charge means greater field, so greater lines will come. Smaller charge means smaller field, so smaller lines will come. So that means here we can conclude one thing, that more lines at a point means more field. Less lines at a point means less field. So the number of lines will depend upon what? Magnitude of charge, not sign of charge. Sign of charge changes the direction, but magnitude changes number of lines. And the field lines cannot cross. Suppose at one point, one field line is this, another field line is this, like this. If they intersect two, then you will get two tangents. Two tangents means at one point two directions for electric field, which is impossible. So that's why we cannot have two field lines intersect each other. So if you take any diagram of field lines, no two field lines will intersect each other. And the closer the lines, the stronger the field. As I said, if the field line, see here if you take, it is near to the charge. That's why field lines are very crowded. Their field is more. When you go away from it, the field lines are far away. As distance increases, electric field what happens? Decreases. That's why here the field strength is less. So here it is clearly representing in the form of field lines. Less field lines, less field. More field lines, more field. And where the field lines are parallel, uniform space, the field is uniform. That means in previous questions also we represented like this sometimes. This is the field like this. See, equally spaced and parallel to lines. This is called uniform electric field. Means everywhere the field is same. So wherever the field lines represent like this, parallel to each other and equally spaced, what does that mean? You consider at any point, same field lines will be there. That field we call it as uniform field. And I will show you all the possible directions. One is for positive charge, how it looks like. And here weaker field. So strength is less because the charge magnitude less. Here strength is more because the charge magnitude is more. The difference between field lines when the charge magnitude is compared. So greater the charge magnitude, greater the field, more the number of field lines. And here it is the diagram like two charges, one is positive and one is negative. So when there is a positive charge and when there is a negative charge, see the field line start from positive charge and for the field line end on negative charge. So that like this it will come. They will not intersect, but they look like they are starting from positive charge and they are ending on negative charge. So like this, the question can be asked based on the field lines in entrance. What kind of field lines look like for a combination of two positive charges or two negative charges, or one positive charge and one negative charge, or one positive charge alone, or for one negative charge alone, like that. So all the combinations I will show here. See here, positive, positive. So if you observe the pattern, the field lines are away from the charges. As they repel each other, like charges repel each other, so they are repelling each other. Field lines also they are not mixing. Here for negative charges also, they repel each other. But here the difference is as they are negative charges, the field is looking like coming towards the charges. The field lines are ending. See here they are ending on the charge. So that is the difference between positive charge field lines and negative charge field lines. Now field lines pattern for electric dipole. Same thing. Dipole nothing but what? Positive and negative charge. Just before we have already seen. If there is a positive charge and if there is a negative charge, how the field lines look like. That combination only we call it as what? Dipole. Now, so here again I have given like a, for the notes purpose just to points whatever we have seen. So please write all these notes. See for positive charge, for negative charge, for positive negative, for positive positive, all the combinations I have given, all the properties I have given, for negative positive, for negative sorry, and for one negative positive but to different magnitudes. So all the possible things and all the possible properties also I have given. So please try to understand. And here as I said, at one point the field lines are closed, at another point the field lines are far away. That means field at A is greater than field at B. Based on this also many times they asked question in entrance. So the concept of field lines is all about in the region of electric field. You can imagine lines, whatever may be the lines, such that they never intersect and at any point their tangent gives the direction of electric field and they are closely spaced means the strength is more and they are far away means the strength is less. So that kind of lines, whatever we imagine to illustrate what is the field in that region, those imaginary lines we call it as electric field lines. Now what you have to remember mainly is what kind of pattern will be there for the field lines in case of positive charge or negative charge or combination of charges. So please try to revise everything and ask me if there is any doubt further. Now based on the same electric field lines, we define one more thing, that is electric flux. So what is the meaning of flux? Flux means number here. What number? Suppose there is a positive charge. Now like this, field lines are going away from it. So there are so many field lines. Now you consider a small region here. Now you consider a same region here. Now you consider a same region here. See here, if you consider there are 3 lines. Here if you consider 2 lines. Here if you consider 1 line. So when you consider a particular area, how many number of lines? Number of what lines? Field lines passing through that area, that we call it as flux. Flux means quantity, number. So what flux here we are defining? Electric flux. Electric flux means in the region of electric field, if you imagine or if you consider a particular area, let's take ds, within the region of electric field, the number of field lines passing through that area or crossing the area, see the total number of electric field lines crossing an area known as electric flux. And that mathematical expression they have given as in this formula, that is flux is equal to E bar dot ds bar. So here the dot product of surface area and the component of electric field perpendicular means, suppose this is the surface area. Now you should not consider the field parallel to it. You should consider the field perpendicular to it. So in this formula, E is perpendicular to surface and ds is some particular surface area. Number of field lines crossing the surface perpendicular to its surface area, we call it as what? Flux. And the mathematical expression for the flux is dot product of electric field and area. Dot product of electric field and area. So what is the dot product of a quantity? See here, electric flux over an area in an electric field is a measure of number of field lines crossing a surface. Number of field lines crossing a surface. It is denoted by pi E, flux, and E bar be the electric field at the location of the surface element ds. The electric flux through the entire surface is this one. Means there is some total surface. We don't know total flux. Suppose if you consider one small area ds, then the small flux is E bar dot ds bar. Then the total flux, this is the small flux through the small area. Then the total flux will become integration of the small flux. That is what here they are showing. But how to use this integration and all, we will study further. Here just the expression I am giving, that for any big surface area when you want to find flux, first you will consider one small surface area. Then you will take the flux for the small surface. Then you will go for the integration. So what kind of situations will come where we use that integration? These all things we study in further classes. So that is what electric flux and its mathematical expression. And as electric flux is a just number of field lines, it is a scalar quantity, or electric flux means dot product, but the result of a dot product must be what? Scalar. And what is the unit will become? Electric field means Newton per Coulomb and area means meter square, or else electric field in another unit also will come, but that we will study later. Now present you remember this unit, Newton per meter square per Coulomb. So Newton meter square per coulomb. So that is what? Electric flux. But here we are telling that electric flux is E bar dot ds bar. Ds bar means what? Area. Area vector. So how to take area vector? So how to take area vector means area vector we will take it in this manner. Suppose this is one area in xy plane. So area is A. So A bar means A. Direction means perpendicular to surface. It is in xy plane means perpendicular is what it will become? Z direction. So what is the vector will become? K cap. Or the area is in suppose YZ plane area suppose A naught. Then A bar will become A naught. YZ plane the surface. Perpendicular to the surface means perpendicular to YZ plane. Perpendicular to YZ plane means X direction. That means I cap. So always you should consider the area vector such that the area direction is perpendicular to the plane of the surface. If the plane is in xy plane, then z direction. If the plane is in yz plane, x direction. If the plane is in xz plane, then y direction. Like that, you must be able to understand what is the direction of area vector. Then only you can solve numericals. And those numericals also we will solve in the further classes also. Because one of the important topic is flux in the entire chapter. Many times they asked a question in the entrance. Now, see here two examples I have given. Just try to understand, which we will discuss even later also. Just try yourself. Now, based on the same flux, one thing they defined that, or one person defined a law, and that is all about Gauss law. What he said is, now we are telling flux. Flux means E bar dot ds bar. So we need to take some dot product, or sometimes we need to take integration we are telling. But here what he said is, not in every case, but if the given question is like there is some closed surface, a closed room, a closed sphere, a closed cylinder, any shape, there is a closed surface suppose, whatever may be the shape, and there is some net charge inside. Then the number of field lines coming out or coming in, whatever it is, that is equal to flux equal to what he said is simply Q net by epsilon naught. He gave one simple formula for this special case. What is that special case? If there is a closed surface, see, Gauss's law in electrostatics is a relation between the charge contained by closed surface and the electric field that crosses that surface. That's why, see here I will show you. See, if there is a particular closed surface. Now for small surface area, the flux is this one. So total flux will become integration. See, for this small area, flux will become d pi equal to E bar dot dA bar. Now the total flux will become integration E bar dot dA bar. But here we are representing one symbol circle here like this. What does that circle represent? Is it is a closed surface. So for this closed surface, what he said is that is equal to, you don't have to integrate anything, you have to take directly that, you have to look at what is the charge is there inside. Suppose minus 1 coulomb, plus 2 coulomb, minus 3 coulomb is there. So what is the total charge now? Minus 1 plus 2 minus 3 equal to minus 2 coulomb. So the flux will become now Q net by epsilon naught, means minus 2 by epsilon naught. This is the flux he said. Suppose for example I will tell you, there is a closed surface, there is a positive charge, there is a closed surface, there is a negative charge. Now the field lines look like they go away from it. Now here field lines look like they coming towards. So here flux means the field lines, number of field lines. They are leaving the surface. They are leaving the surface. So that's why he said flux leaving. Flux leaving is due to positive charge. That's why you take positive. And flux entering the surface is due to negative charge. That's why he said flux entering means negative. So flux leaving or flux entering. Flux may be positive, flux may be negative. Flux is positive due to positive charge, flux is negative due to negative charge. Flux positive means leaving the surface, flux negative means entering the surface. That is what we need to understand. Now, so what is the flux? What is the field line? What is the Gauss law? So in a region, in a conclusion, in a simple way, if you consider, there is a region and some field lines are there, something. So that means there are some charges and they are producing some field at every point, and that we are imagining in the form of imaginary lines. Those lines we call it as electric field lines or electric lines of force. Electric lines of force also you can say. And in that region, if you consider one area, the number of lines passing through that area perpendicular to surface area, that is called flux. And if you imagine a closed surface within that, any region, if there is a closed surface and the total flux depends on the total charge inside. Suppose there is a charge Q1, Q2, Q3 outside. Now the flux does not depend on Q3. Flux depends on only Q1, Q2, he said. That is what the statement given by Gauss's law. So the total flux for any closed surface depends only on inner charges, not on outer charges. So for everything we have taken definition and introduction, for which the same thing will continue in the coming class. Because these all things are interlinked, and how to study and how to do, how to solve all these things, we will continue in the coming class. So please try to take each and every definition. Try to read all these notes. So make your own clear notes for each and everything. Then we will continue. So here I have given few points like Gauss law holds good for any surface regardless of its shape. As I said, shape is not matter. It's not like it should be sphere or cylinder. Any shape. The condition is it must be closed. But if it is not closed, what will happen? That we will do later. That is what this point. This point we will not understand here now. So what is this point? What is Gaussian surface? We will study later. Because we said here there should be a closed surface. But sometimes they create question without closed surface. Then how to calculate? We will understand later. Now for any closed surface, if there is a net charge, then only flux will be there. If there is no net charge, no flux. Suppose minus 1 coulomb plus 1 coulomb is there. So what is the net charge? Charges are there. But Q net is how much? 0. Q net 0 means flux is also how much? 0. Field lines are there, but they are getting cancelling. So that is what the Gauss's law says, that for any closed surface, Gauss law says only about closed surface. Now we will study what is Gaussian surface, how to find flux linked with a surface, application of Gauss's law, how to connect these things, all those things. So here whatever definitions, whatever introduction we have taken, please try to understand and try to remember each and everything. If there is any doubt, please message me. So we'll continue in the coming class. Thank you all of you.